Okay. So we have talked about the concept of state in the previous class. So what did we do in the previous class? We talked about probability. We talked about what is a dynamic decision process. How do you know whether a decision process is a static decision process or a dynamic decision process? If your current action influences the future observation, then it's a dynamic process. If your current action does not influence the future observation, it's not a dynamic problem. Okay, so the only way you know something is dynamic or not is if your current action influences the future observation. Okay, and then we talked about the concept of state, a topic that is not emphasized in most of the reinforcement learning classes, but I think it's an extremely important topic for you all to master, especially because I assume many of you would be going to industries such as Amazon and Google, and you will be implementing reinforcement learning algorithms. And you need to be able to specify the state space very well on day 1 or day 0 so that you can actually solve the problem on day 365. Okay? If you get your state space wrong, you will be on the wrong path for a very, very long time before you realize that your state space is wrong, and that's why you're not able to solve the problem using reinforcement learning. And one of the things that I'll tell you from my personal experience, we were solving a problem in reinforcement learning back in 2016, and we were looking at optimizing autonomous vehicle path at that point of time, and one of the things that the student omitted from the state space was the heading of the vehicle. It was just not part of the state space, and we spent 1 month trying to fine tune the code so that the car learns how to drive on a road, and it did not. Okay, and as soon as we put heading as part of the state space, it started working. So 1 month was spent trying to troubleshoot the code which was working perfectly fine, just because the state space was not comprehensive enough for our problem. Okay, so it's important. State space is extremely important. What did we talk about the state space? So we want the state space to satisfy 2 properties. So the first property is, okay, maybe I'll introduce another variable called history. So history, I'm going to define it as h of t. This is I0, A0, S0, I1. I think we were using not A. A is not used for action, right? U is used for action. Yeah. Can you check your notes? U is for action. Okay. U0, U1, S1, I2, U2, S2, all the way up to IT minus 1, UT minus 1, ST minus 1, and then IT. So I have all the observation, action, state, observation, action, state, observation, action, state, and the last one is the current observation. So that's my history. That's the entire history. So history at time t is everything that I have seen so far, including the last observation that I've made about the state, about the system. So that's my history, and the state st should satisfy the probability of st plus 1 given ht. Okay, maybe I should not make it t plus 1, is the same as probability of st given st minus 1 and ut minus 1. ut minus 1 and st minus 1.
Wait, so u, not v, right?
Not v, not v, u. This is also u. So that's number 1, that's the first criteria. And the second criteria is probability of cost at time t given ht maybe t minus 1. Let me put it as t minus, let me think. Should I have t minus 1 or t? Let me put it t minus 1. That's good enough. So the cost at t minus 1 given the entire history should be a function of just the state and action at the previous time step. Okay, now there are, like we had mentioned, I can use the temperature of the moon or the color of my shirt as part of the state space. I can augment the state space with a lot of random stuff. But what you want to pick is the minimal such ST. You want to pick, you always want to pick, you can always expand the state space, you can add a lot of stuff in it, which, and these two criteria will still be satisfied. But you don't want to add too many random things in your state space. So your state space has to be the minimal variable that satisfies these two conditions. So ST should be minimal. And when we talk about universal function approximation towards the end of the class, probably in early November, I'll tell you why sometimes it's good for ST to not be minimal. Okay? So for until November, we want ST to be minimal, and in November we'll talk about why ST should not be minimal. Okay? So I'll give you both the perspectives by the end of this class, end of this course. Okay? So any questions on this? Yes, please.
What is the A?
Oh, I'm so sorry. This is you. This is the action. So unfortunately, because I'm using different references, sometimes S is used as X, U is used as A. So I'll mix it up on the blackboard, and please do correct me. It'll also help me know whether you guys are awake or sleeping in the class. Okay? So if you point out mistakes, you will get brownie points. Okay, any other question? Yes, please.
So I is observation and S is state.
That's right, this is the observation.
It's like POMDP definition or
Not yet, we'll get into, I don't think we'll talk about POMDP in this course. Okay? We'll always talk about perfectly observed MDPs.
In general, is the state usually be observed or it can be latent?
Yeah, so that's what his question was, whether the state is observed or it's not observed, whether it's partially observed. So in this particular course, we will only talk about fully observed MDPs and fully observed problem statements. The way you solve a partially observed MDP is you convert it into a fully observed MDP with a much more abstract state space. Okay? But we won't talk about it in this class. It requires a bit more complicated machinery to work with. Okay. Any other question? Okay. So the two questions that were just asked are very important questions. So are we always going to be able to observe the state or not? So if you go back to the Amazon's recommendation system example, Amazon doesn't know much about me. Well, in some sense they know a lot about me, but in some sense they don't really know a lot about me. So they know my address, they know my purchase history, they probably know my income to some extent, because from address they can figure out the value of the house, and from that they can figure out what my income or household income approximately is. So they can figure out a lot of information about me. But the real issue is, if you look at the Amazon's recommendations, you will find a lot of issues with the recommendation. So I'll give you one specific problem with Amazon's recommendation, which is if I have bought a iron from Amazon, it'll keep showing me recommendations about the iron, even though I've already bought it. How many times would you buy an iron in your entire lifetime? Maybe 3 or 4 times. There's no point of Amazon spending their real estate to show me different irons that I could have bought instead of the iron that I have bought. And yet they will keep showing me recommendations about it. So in some sense, their description of the state space is not encompassing enough to know that once this person has bought a specific item, that person may not need that specific item for another 10 years and therefore not recommend that item to him or her for the next 10 years. Okay? So it's a partially observed situation, and in partially observed situation, you have to, again, the way you define the state space has to be careful, because even though Amazon knows a lot about me, they don't know everything about me. They don't understand the dynamics of my brain. They don't understand what I'm going to buy next. As a result of which, it's a partially observed system, and the current state space that they are using for the recommendation system is not encompassing enough. In some sense, it is too minimal. It is too small in order to capture my purchase history and convert that into a recommendation for an item that I'm going to buy. Okay. Perfect. So we'll talk about fully observed MDPs in this class. And what that means is I have identified the right state space ST, and I can use the observation to reconstruct ST. So I can use IT to reconstruct ST, and therefore, or I can use this history to construct ST. So that way I'm in a fully observed situation. There is no ambiguity about which state I am in. In the partially observed case, that is always a problem. You don't know which state you are in. But in fully observed, you can reconstruct the state completely, as a result of which there is no ambiguity whatsoever. So let's talk about the case where IT is equal to ST. So the observation is the same as state. UT, of course, we know. And then there are a few things, a few notations I wanted to introduce. And these notations are from this book, Markov Decision Processor. It's a classic book written back in 1993 by Martin L. Puterman. MDP. So I think this book is in the library. If not, and if you're interested in MDP, I think you should buy this book. It's a good reference. So I'm going to be using some results from this book in this class and the next class, and probably like 3-4 classes. For the next 3 or 4 classes, I'm going to be using contents from that book. So I have IT, which is the state. So observation is the same as state, or in other words, I'm observing the state completely. And so PIJU is a transition matrix, state transition matrix, which is given by the probability that IT plus 1 is equal to J, given IT is equal to I, and UT is equal to U. So it's a state transition matrix, and then CIUJ. Cost function, and this is the cost of being in state I, taking an action U, and transitioning to the next state J. So that's the cost represented by this cost function. At current state I, action u next state j. Yes, please.
A quick question: like, why the history of the of time of state t doesn't include the state of time t?
It includes the observation of time t, but not the state at time t.
Okay, so because we don't know the state of the time, we just know the observation of the time.
That's right.
Okay.
State is something that needs to be defined. So if you're just observing, you may not have the complete information about the state.
Okay.
Okay? So now we are moving to a situation where we have complete observation about the state. So this is a more this is the way the state is defined. Now we are moving to a case where the state is always defined and you know what the state of the system is.
Yeah, that was like fully observed MBT. Like we are right. We know the IT, then we know the ST.
Yes.
Okay.
Yes.
Continue from his question. If
Huh.
fully observed MDP IT equals ST, so IT should be removed from HT, right? Because IT.
That's right. Yeah. I mean, yeah.
Thank you.
Yeah. Definitely. Any other question? Yes.
So will this cost function related to the loss function in the future?
Yeah. So in reinforcement learning literature, either you have reward function or cost function. You can call it a loss function as well. It doesn't matter. It all means similar thing in the sense that all of this leads to defining what is known as the performance index of the MDP, which is what I'll be talking about right now. So there are many performance index of the MDP. Let me write down those performance indices. So finite horizon cost, J of something, that something is okay, we'll introduce what J is a function of in a bit. So this is expected value of summation t equals 0 to capital T, Ct, it plus 1. Oh, I should be using ST, right? I'll use ST. Okay, so there are different indices, the different performance index that you want to optimize depending on the situation at hand. So in the evening after the classes are over, I have to go back home, and there are segments of the road. So sometimes I'll be on a highway, sometimes I'll be on city road, sometimes I'll be within the university premises, so there'll be a lot of people walking around. This is the cost function that I'll be trying to optimize at that time. It's a finite horizon. I'm going to get home in 20-25 minutes. Okay, so there is 25 minutes interval, and I want to make sure that I drive my vehicle so that I optimize the fuel consumption of the vehicle over the next 25 minutes by the time I reach home. The terminal state is going to be the position of my house. Okay, so once I reach the position of my house, there is no further cost that I'm going to incur. So the terminal cost is going to be 0, and there will be a running cost which depends on how fast I am driving, what kind of vehicle I am driving, and what kind of roads I am driving on. Okay, whether it's a highway versus city road, whether it's a stoplight versus not a stoplight, and so on and so forth. So this is a time varying cost. So the cost depends on time, and there is a terminal cost associated, and there is a finite amount of time that I'm going to spend doing that particular activity. And I want to optimize, I want to minimize the total cost, total finite horizon cost that I'm going to incur while solving that dynamic decision problem. Now, there are some cases where I care about the transient states. Okay, so what does transient mean? So if I'm behaving in a certain fashion, I want to make sure that the next few days or next few time steps I'm doing very well, and I don't quite care a lot about the future. Okay, so right now when I'm creating my lesson plan for this class, I care a lot about what I'm going to talk in this class and tomorrow, next week's class, and so on, but I don't really care about what I'm going to talk about in November and December. At least at this point of time, that's not my problem, right? So in those situations, I'm going to have a discounted cost where this is the cost I'm going to incur, but I'm going to discount it by a factor alpha raised to t, where alpha is strictly less than 1. Okay, so if you care about the transient state, if you care about the immediate future, and you don't quite care about the far future, you want to be solving this discounted cost problem. So the cost is not a function of time anymore, the cost is stationary, but I have discounting, which means that, you know, if my alpha is 0.9, so if alpha equals to 0.9, what is alpha raised to 10? Can someone punch in on a calculator and tell me what 0.9 raised to 10 is? What 0.9 raised to 10? Point 35. Okay. What about alpha raised to 100?
E minus 1.
2.6 e minus 5. Okay, so at time t equals to 0, alpha raised to 0 is equal to 1. So I take the entire cost into account. At time t equals to 1, my cost gets multiplied by 0.9. At time t equals to 10, my cost gets multiplied by 0.35. So it still has some value, but not as much as the current cost. And at time t equals to 100, the cost gets multiplied by 10 raised to minus 5. It's pretty much negligible. Okay, so that's discounted cost. In the total cost, there is a steady state that we will reach, and then we will not be transitioning from that state any further, and the cost at that particular state is always going to be 0. So there is it's called an absorbing state. So you get to an absorbing state, and after that the state is never going to transition. So death, for instance, death in organisms, for instance, is that terminal state. So you go through life, you die, and after that there is no state transition. Okay, so there is no state transition, there is no cost incurred. So that's a total cost problem. So there is a notion of a terminal state. You reach the terminal state, and then the state never transitions. And in those cases, we want to do this total cost minimization. So if I'm sending packages from one point to another, once the package reaches the destination, it's a terminal state. Okay? Then there is no further state transition that's going to happen for that particular package. All right, and then there is an average cost case. So in average cost case, the entire cost is equally weighed. Okay, so the equal weigh is 1 over t. That's equally weighed, and then I'm going to let t go to infinity. So I'm going to do the average cost problem. I'm going to solve the average cost problem. This is the case where I care about the steady state as well. I want to make sure that even if I'm doing bad in the transient case, I want the steady state to be perfect. I don't want to have any suboptimality in the steady state. So this is the case in wireless systems, because you want, so when you are communicating at 1 gigahertz, 1 Gbps, 1 gigabits per second, actually you reach 10 raised to 9 time step within 1 second. Okay? So within 1 second, your t will go from 0 to 10 raised to 9, right? So you are basically, if you don't want, you want to create your communication systems in a way that you optimize the average cost, because you actually reach 10 raised to 9 steps within a second, or within a minute, or within an hour. And that's the case where you care about the average cost problem, because the steady state matters, and you are going to reach the steady state in a matter of a few seconds or a few minutes or a few hours, and that's important to you. So if you're doing energy optimization, you typically are in a finite horizon setting. If you are doing Amazon recommendation system, you are in a discounted setting. You care about the next recommendation. You don't care about recommendations 1 month from now. If there is a notion of terminal state, you want to solve this total cost problem. And if there is a notion of steady state and you want to optimize the steady state performance, you solve the average cost problem. Now the question that remains is, what exactly are we optimizing over? So we kind of understand that we have to make a decision at every point of time, and I'm going to be observing the state st before I make the decision. So what exactly is it that I'm optimizing? Like, what's the quantity over which, what's the variable over which we are optimizing? And so I want to introduce this concept of policies / strategies. So all of this J is a function of what is known as a policy or a strategy or a decision law or a control law or a decision rule or a rule. Okay, so all of these are used interchangeably depending on which literature you are referring to. Yes, please.
Is there any restriction about the functional form of the cost function?
So very good question. So right now we are in somewhat of an abstract setting. So the state could be anything, observation action could be anything, and the cost function could be anything. In the most general situation, you want all of this to be metric space and the cost to be measurable function of the state and action. But right now, we'll just focus on finite state, finite action for the next 1 month, 1.5 months. And we'll set up the entire machinery with finite state, finite action. So all of these quantities would just become matrices or tensors. Okay, so 2-dimensional or a 3-dimensional matrix. Okay, so right now think of it as a finite state problem. So there are only finitely many possible STs, finitely many possible UTs, and so on. So the cost function becomes a matrix, and the transition kernel also becomes a matrix. But when we get to the continuous state, continuous action MDPs, which is towards mid-October, will be a bit more general in those situations. Yes, please.
Is there a reason you choose to do the cost function like as a function of the state instead of the observation?
Right. So in this, so right now we have made the assumption that the observation is the same as state, right? You can make it a function of observation. It's just that all of those situations will get into POMDP's domain, and we are not going to be talking about POMDPs in this class, in this entire course. POMDPs is a bit more abstract topic, requires a lot more machinery, so we don't want to talk about it in this class. But it's an important problem. Yes.
Does the cost function have to be stationary for the discounted?
For the discounted, total, and average, yes, the cost function needs to be stationary because then a lot of beautiful results come out of the MDP literature. In the finite horizon setting, the cost can be time varying. But here the cost is stationary, cost is stationary, cost is stationary. Okay, it doesn't depend on time. Any other question? Okay. So what's a policy? Like I said, there are many names for this. So let me write a few names. You don't have to write it. Decision rule, rules, policy, strategy, anything else? Control law. So depending on which year, which book. So if you go to 1950s, they'll talk about control laws. If you go to papers written in 1990s, they'll talk about policies. If you look at the papers from 2020s, they'll talk about strategies. So it's all the same thing. Okay, they mean the same thing. And there are many ways to construct policies. So let me write down the first one, history dependent randomized policy. Here mu is a function of mu t is a function of ht to probability distributions over u. So this is so mu t takes into account the entire history up to time t and then spits out a distribution over the actions that needs to be taken. And I have history dependent deterministic policy. Here mu t goes from ht to u. Then Markov randomized policy, which is mu t is a function of s to delta u, and then Markov deterministic policy Okay, the four policies are completely different. The first policy, we take the entire history and we spit out a distribution over action. So I look at, so let's say I want to optimize what I'm eating for breakfast. I look at my entire history of breakfast that I've eaten so far since my birth. Okay, so I look at that whole, so I'm around 40 years old. So I look at 40 years worth of data of what I ate for breakfast. And then I say that with probability half, I'm going to eat a sandwich tomorrow, and with probability half, I'm going to eat an oatmeal, a bowl of oatmeal tomorrow. Okay, so that's this policy. And somebody says, you know, this is very random. You need to be more deterministic in life. So then I'll say, okay, fine. I'll look at the entire history of whatever I've eaten for the last 40 years for breakfast, and then I'm going to eat whatever I have eaten yesterday. Okay, so I'm going to eat a sandwich. So that's a deterministic policy. With probability 1, I'm going to eat a sandwich, okay, after looking at the entire history of stuff that I've eaten so far. Markov randomized is much better. So this one is saying I'm going to look at what I ate in the morning today, and I'm going to spit out a probability distribution over what I'm going to eat tomorrow. So with probability half, I'm going to eat sandwich. With probability half, I'm going to eat oatmeal. And then Markov deterministic is the best policy ever. You look at what you ate today, and then you come up with a deterministic quantity of what you want to eat tomorrow. So today I ate a sandwich, so tomorrow I must eat oatmeal. If today I ate an oatmeal, tomorrow I'll eat a sandwich. Okay, so this is the simplest strategy, simplest policy that you can have. This is the most complicated policy that you can ever imagine. Okay, and the question is, what is the policy over which you want to optimize these performance index? Generally speaking, if you are looking at an optimization problem, the larger your space, the variable space is over which you are optimizing, the better it is. So arguably speaking, if this is the performance index you wanted to optimize, if you optimize over this, you will get the best possible performance, so the minimum cost. If you optimize over this, you will probably get a worse cost, right? Does that sound reasonable? So this is very, very complicated policy space, so it's very big space. I'm optimizing a function. Optimizing a function over a big space means that you will have a much better chances of getting a lowest cost possible. The surprising thing about the Markov chain theory or Markov decision process theory is that for every policy that you can pick here, there is going to be a policy in the Markov deterministic category that's going to beat the performance that you get out of this. Okay, that's the big result. We'll talk about this result in this class and the next class under whatever assumptions that are needed. But basically, it has to be a stationary MDP. So in the case of a stationary MDP, or even in this case where the cost function is time varying, it's always better to pick a Markov deterministic policy because you will get the best cost within this category. So there's no point talking about whatever I've eaten over the last 40 years. Okay, does that make sense? Yes, please.
Then if the setting is like multi-agent setting, then isn't it that randomized policy is better?
Right. I get this question every time. So it's a very good thing. So what are the situations? So think about your own life. What are the situations where you have actually randomized, where you have not declared what action you are going to take and you are going to randomize? Can someone come up with an example where you randomize? So sometimes you randomize because there is ambiguity. You don't know what the future holds, so you are going to randomize. So you don't know where you will end up after getting your master's or a PhD degree, so you take a bunch of courses, right? So you randomize. The other case where you randomize is because you are in a competitive setting with respect to the other person. So you are playing table tennis, you're playing football, you're playing basketball, you're playing chess. You have to randomize. You don't want your adversary to predict your actions. And in those cases, you use randomization. So in a multi-agent setting where you are competing with other people, you randomize. Again, that's not the topic of this class. I have taught game theory, and those lectures are on YouTube, where we talk about randomized strategies all the time. But in this particular class, we are not going to talk about randomized strategy because we are not going to be talking about multi-agent systems, and we are not going to be talking about competitive settings. Okay, but there are reasons why you would randomize over actions, valid reasons, and that's ambiguity or multi-agent settings where you have to randomize. Great question. Any other question? Okay. So a strategy is a collection of these policies all the way up to mu infinity. So you go from mu1, mu0, so the strategy at time 0, strategy at time 1, strategy at time 2, and so on and so forth. Collectively, we'll call this a strategy. And we'll denote it by mu hr, mu mr, mu ht, mu md. So history dependent randomized, Markov randomized, history dependent deterministic, and Markov deterministic. Okay. So the results, the various results, again those results are from this book, Futterman's book on Markov decision processes. For every mu hr, there exists mu md, sorry, not md, mu hd, such that j mu hr is greater than or equal to so for every are you guys familiar with this notation? For every, okay, there exists, perfect. So for every policy that is history dependent randomized, there exists a policy which is history dependent deterministic, such that the performance index with the randomized policy is greater than or equal to the performance index with the deterministic policy. This is all in chapter 4 of the book. For every mu ht, there exists mu md such that so for every history dependent deterministic policy, there exists a Markov deterministic policy. Let me just put it this way, because they solve they come up with even better solution. So so what the upshot of these two results is that you always want to pick a Markov deterministic policy and you want to optimize over a Markov deterministic policy. So you have your performance index and you want to minimize over all mu, which is in the Markov deterministic class of j of mu. This is our main problem. Yes.
Could you explain, I mean, a little bit more why the theorem 2, like why
The first one,
not theorem 2?
second one. We'll talk about it in the next class. Okay, we'll prove this result This result, I'll prove it in a hand-wavy way. This result, I'll prove it rigorously in the next class. Okay, we don't have the time in today's class to go over it. Yes.
About theorem, if determinist policy can be viewed as a special case of random policy, so theorem is immediately, can I view it this way?
Right, but remember we were saying that this is a richer class of policies, so you might be able to get a much better result, right? But turns out that you can always improve upon it by picking a deterministic policy. Do you see that? Yes.
I think it's counterintuitive because the deterministic one is a subset of the random.
That's right.
So how can it improve?
Right. So what you do is at every history, so the answer to that is you pick in the, so you pick the history dependent deterministic policy at time t at history ht as the minimum value. So you pick the support, you look at the support of AT in the support, not AT, UT in the support of mu HRT HT, and there is some cost function that you optimize. So you look at only the actions that are in the support of the randomized policy at time t evaluated at the history ht, and then you pick the one that minimizes the performance index, and that's how you get the history dependent deterministic policy. So I'll get to it in the next class because it requires parsing through a lot more notation, so I want to be simple in this class. Okay. So both of these results are from chapter 4 of Putterman, and we'll go over it in the next class. Okay, so what are we given? We have a transition kernel Piju. I have a cost function, either it is time varying or it is stationary. So this is time varying, means in a finite horizon setting I have a time varying cost function. In an infinite horizon setting or a total cost setting I have an invariant cost function. It doesn't depend on time. So I'm given this state transition kernel, I'm given the cost function. I want to pick the policy mu, which is in the Markov deterministic category, and I want to optimize this performance index. Okay, that's the problem statement given to us. This was the problem statement studied all the way from 1950s to 1980s roughly, and 1980s onward the situation turned a little bit. So remember, knowing the state transition kernel means that you can model the system. You know what the physics of the system is, you know what the biology of the system is, you know the chemical processes that are driving that particular system, and so you know the state transition kernel exactly, and you know the cost function exactly, and therefore you can solve this optimization problem using what is known as Bellman's principle of optimality, which I'll be talking about next. Okay, so you use dynamic programming to solve this problem. What changed in 1980s was a lot of data started getting generated. Okay, so you created a battery system, and now the battery system is generating the data about the input-output voltage. You don't understand the underlying chemistry of what is happening inside the battery. You have some idea, right, but you don't have complete idea. You have people are treating cancer patients. Okay, so you don't have all the information available about how the drug is interacting with the bloodstream, and how does that bloodstream interacting with the lungs and with the livers and with the kidneys and so on. But you are collecting the data about whether the person is getting treated or not getting treated using that particular drug. You have Amazon, which doesn't know about people, which doesn't have a physical model of people's brain, but people are buying stuff from Amazon, and people are putting 5-star reviews versus 1-star reviews on Amazon, and going again and buying something else from Amazon. So a lot of data is getting created. So I don't know what this transition kernel looks like. I don't know what this cost function looks like, right? But I still want to solve this problem. Okay, and that's the reinforcement, that's the topic of reinforcement learning. So the way reinforcement learning differs from what happened pre-1980s was, in reinforcement learning, we have the data and we do not have the model. Okay, and you can have any combination. You may not know the cost function, but you know the transition kernel. You may not know the transition kernel, but you know the cost function. Or you know the transition kernel, but you may not know the cost function. And in all these different situations, you have different reinforcement learning algorithms that will help you get the solution to this particular problem. Okay? And one thing that you have to be aware of, or you have to be careful about, is how much data is needed in order to solve this problem reliably. So do you need data for 10 days? Do you need data for 10 years? Do you need data for 1,000 years? So that's the part that depends on the complexity of the reinforcement learning problem, and something that we will be talking about in the subsequent classes. Okay. So how many of you have studied dynamic programming before? How many of you have not seen dynamic programming before? Okay, a few people. Okay, so I'll talk about dynamic programming now. And I'll talk about how to solve this particular problem. Okay? For now, we'll assume that theorem 1 and theorem 2 are correct, and we'll solve this problem, and in the next class, we'll go back to theorem 1 and theorem 2. So I'm going back to 1949/52, maybe 51. Okay. So somebody had to solve this particular problem. Somebody was given this job of solving this problem. The person was Richard Bellman. And so he wanted to solve this problem. And so he came up with the Bellman's principle for optimality, which basically said, so I'm looking at the finite horizon setting. So he came up with a theorem which is known as Bellman principle for optimality, that mu naught to mu t, let me put a star here, is optimal if and only if mu t star to mu t star is optimal for every sub-problem starting at time t. And this is for all t.
That means for all t greater or equal to 0, right?
I mean, yeah, it's a finite horizon and t goes from 0 to capital T. So by optimal, what I mean is I want to find the minimum cost, so that's the optimal solution, that's mu star. So it's saying that mu 0 to mu t star is optimal if and only if you look at the truncated policy, it is optimal for the truncated problem. Okay, and the way you get the algorithm, the dynamic programming algorithm, is by applying this theorem. So your mu t star S capital T is minimum over all U capital T of C T S T U T S T plus 1. I guess I have to do summation over S T plus 1 plus C T plus 1 S T plus 1 probability over S T plus 1 U T. So this is my expected value. Remember, I'm in a finite state, finite action setting, so that way I can keep things simple here. So I look at the expected cost, and I'm going to minimize the expected cost with respect to UT.
Because I'm confused. The big upper T is the terminal state, right? Terminal time.
Terminal time, that's right.
So why would we still have a sigma ST? Sorry.
Yeah.
Sorry.
ST plus 1, that's the terminal cost. Okay, this is the recurring cost, this is the terminal cost. Okay, so I get the optimal policy at time O. I have written it as min, but it should actually be argmin. So that gets stored as policy, and I'm going to define Vt star of St. This is my value function. Which is stored as Vt star of St, and that's my argmin. That is actually the minimum. So the minimum value is stored in the value function. The argmin is stored in the policy. Okay. So what I get is a value function. So after doing the optimization after solving the sub problem at time capital T, I get a policy, optimal policy, mu t star. But I also get another variable, another function, which we are going to call value function in this class, right? And the value function stores the minimum value, whatever is the minimum value of this particular objective function. Any questions so far? So we have an argmin and we have a min. Argmin gets stored in the policy, min gets stored in the value function. Yes?
So since it's upper T, so we are defining on the last step.
On the last step.
Only after.
Only the last step, yeah.
Thank you.
Right? So I want to find this optimal policy, right? That was my problem statement here. So it is optimal if and only if this thing is optimal. So let's just look at the capital T and find out what this mu t star looks like. Now that I know what mu t star looks like, I can go back and figure out what mu t minus 1 star looks like. So let me write it here. Okay, so mu t minus 1 star s t minus 1 equals to argmin u t minus 1 S t minus 1 S t
under the sigma.
This is S t, that's right. Thank you. So that's my policy at time t minus 1, and I'll have Vt minus 1 star St minus 1 equals to min of the same thing. So the cool thing here is instead of looking at the entire subproblem, which will go all the way up to time capital T plus 1, I can replace the last part of the subproblem with this value function. So this value function appears in this equation as a terminal cost. And I can keep going on and on. So I did this for t minus 1, I can do it for t minus 2, I can do it for t minus 3, all the way up to time 0. And because each of the policies are is optimal for the subproblem, by construction, what I get is that this mu naught star all the way to mu t star is actually an optimal policy for the finite horizon problem. Yes.
I just want to answer like why not why, but I'm confused about the PST minus 1 ST is the probability of
Transition kernel at ut minus 1.
oh yes,
Right? This is the transition kernel of going from st minus 1 to st if I pick an action ut minus 1.
But I don't really understand, but why we have to use this transition measures here?
Oh, because you have this very big sequence of policies that you want to optimize. That's a very big optimization problem. This is a way to decompose that optimization problem into a step of one-step optimization problems.
Okay, so it's like step by step.
Step by step. So this is what you want to find. It's a very complicated problem. This is something that's doable. It's something you can execute on a machine. So you can execute this problem, then you get to this, then you execute this problem, then you get to the next t minus 2 stage problem, and then you solve that, and so on and so forth. So you have a very complex problem that gets decomposed into a sequence of simple problems.
So it seems like a backward process because due to
It is a backward induction
So it's
process.
Like, it should be the capital C or it should be the capital T or it should be the small.
Here it is capital T. So you start with capital T,
From last step, this is second last step.
then this is second last step, then you go to third last step, and so on. It's a backward process, not a forward process. Okay? So this is something that I go in greater detail in my optimization class 5500, but I'm sort of rushing through it here. Okay? So we have 5 minutes left. Can someone tell me why Richard Bellman was interested in this problem? What was happening in 1940s or 50s? What was interesting about 1940s and 50s? And why were people into optimization so much? Why were people into dynamic optimization so much? What happened in 1940s that led to this dynamic optimization? Yes?
Computers.
Computers to some extent, but there is something more to it than just computers.
Nuclear.
Huh? Sorry?
Nuclear.
Not nuclear. I mean, it has something to do with World War II, but not quite.
Stock, right?
Sorry?
Stock.
No.
Cold War.
Sorry?
Cold War.
Cold War? Yeah, it has something to do with Cold War. What was happening in Cold War?
That was rocket, something like that.
Yeah, it is related to rockets. So there were two things that were happening in Cold War. One is aerial combat. You want to make fighter planes fight with each other, right? So that was studied by Isaacs. So Isaacs is not known as the person who came up with dynamic programming, but actually he was the first one to come up with dynamic programming in 1949, but that was a confidential document. But what Richard Bellman was interested in was sending rockets to space, because space was a big thing at that point of time, and people wanted to send rockets to space. Sending rockets to space is an expensive activity. And why is it expensive? Because of the fuel, right? So rocket have to get to the escape velocity in order to get out of the Earth's environment, right? So you want to use as low fuel as possible. In order to send the rocket to space, it was a matter of pride for the US as well as for Russia or USSR at that point of time. So that's why both sides of the equation were interested in sending rockets to space. Therefore, both sides were studying dynamic optimization, and both sides came up with some algorithm to solve the problem. So on the US side, Richard Bellman came up with the principle for dynamic programming. And on the USSR side, Pontryagin came up with the maximum principle. So that's something I'm not going to talk about in this class, but that's something I cover in great details in 5500. So those of you who are enrolled in 5500, you would see that towards the end of this, this semester. Okay, so that's why we are picking up what Bellman did for the rocket industry, and we'll take this all the way to what Amazon is doing today. Okay, so that's all I have for today. I'll see you on Tuesday of next week. If you haven't marked your attendance, please do come back to me and mark your attendance. Thank you so much. Just give me a second, I'll turn off the camera.